Greetings, calculus scholars. Thank you for joining me today. We're going to be doing skill 11 today, which is the definition of a derivative in terms of limits. So before I start this lesson, I do want to give you a warning. The limit definition of a derivative is kind of a rite of passage, and it's something that's going to give you a really rigorous understanding of derivatives. It is not the easy way to compute derivatives, but it's going to give you a connection to our limits unit, and it's also going to give you a more intuitive and conceptual understanding of derivatives. And I'm doing this because I believe in you guys, and I'd like to, give you the challenging work and the beauty in the calculus on this. So I will say that this is a skill, and starting with the next skill, you will see that there is a much easier way, and you will probably kill me for not introducing it first. But I want you to see in action how we're using our limits to actually find and connect the secant line with the tangent line and the equations. I want to go back to one of my favorite Delta math exercises of all time, something that you worked on about 2 classes ago. This was the secant line limits graphically. And what this activity was, and why I loved it so much, is it had you explore secant lines, and your goal was to create a secant line that best approximated what the slope of the line was at that yellow point. So this H thing is the difference between my X values. So like at this point, the difference between my top X value and my lower X value is 3. And as the H gets lower and lower, your secant line starts looking more and more like a tangent line. So now I'm pretty comfortable, so I'm going to zoom in. And I'm going to zoom in even more. So now the H is like 0.02. So it's getting really, really, really close to 0. And you may notice here that there's this average rate of change formula. So we're taking the -1 plus the H factor minus the f of -1 itself divided by the H difference. And we want that H difference to be as close to 0 as possible. Now we're at 0.002. And I'm going to guess that the derivative is about 1. So the slope of that line is about 1 for the derivative. So that exercise, I think, gives people actually a really good background as to why we do the limit definition of derivative and where it comes from. So here's the limit definition of derivative. So our goal is to get that H as close to 0 as possible. So you want the distance between the X values of your secant line as close to 0 as possible. So this is your pretty much like your average rate of change. And then this is the, this above formula here is your limit definition of a derivative. So let's take a look now at actually doing one and see what happens. I don't have like very good equation editors on PowerPoint, but really what's going on here is you have the f of x is equal to 2x squared minus x. So I'm going to write the limit as h approaches 0 of f of x plus h minus f of x all over h. So we want that h to get as close to 0 as possible. So just a little side note here with this f of x plus h. What this means is you're just going to be putting in the x plus h. Like this would be 2 times x plus h squared minus x plus h. And there is a lot of multiplication that you have to do. But it will be very well worth it. So I'm just going to do the x times the x to get x squared. And then I have 2xh's. And then I have a h squared minus x minus h. So that's going to be 2x squared plus 4xh plus 2h squared minus x minus h. So that's my f of x plus h. And then the f of x is already kind of provided. So I like to kind of just do them separately. So then I'm just going to put this in, and there's going to be something really beautiful that happens when we do this. So I get 2x squared plus 4xh plus 2h squared minus x minus h. And then I have a minus a 2x squared minus x. So you really want to make sure that you are keeping track of the negative sign as it distributes. So this is the f of x plus h, and then that's the f of x. So we're going to have a limit as h approaches 0. So this 2x squared and the minus 2x squared cancel out. Actually, I'm just going to just distribute the sign first. You don't have to do this step after you're a little bit more polished. But the 2x squareds cancel. So I'm left with a 4xh plus, and the minus x and the positive x cancel, 2h squared minus h over h. And I'm just going to actually be able to pull out an h. So all your terms should have an h left in it. So that's why I can do this. So I'm going to get 4x plus 2h minus 1. and these cancel out. So then I just plug in 0 for h. So I have 4x plus 2 times 0 minus 1. So that's just going to be 4x minus 1. And that is the equation for my derivative. Whew. So in summary, you really want to get practice with like the function composition. So you're plugging in, and if you're kind of a little bit rusty with that, here's what I would do. So I'd write, 2x squared minus x. And if you want to do the f of x plus h, you do the 2 times x plus h squared minus the x plus h. So you can see like how we plugged it in. And I would just do that part, separately. And then you can just substitute that into the limit equation. The f of x part's pretty easy to substitute in, so you don't have to do a lot of work on that. And you're doing this correctly when you can like pull out an h so that the top and the bottom can cancel. And this gives you the derivative. You're going to actually learn a way that's a lot easier next class. And we're going to be doing that much easier way. But this gives you that conceptual understanding of what a derivative is. And that's really like a secant line where the x value differences get as close to 0 as possible. All right, so one thing that you will be asked in Delta Math today to do is move to something, so that derivative is 4x minus 1 that we computed. So you may be asked to use that derivative to find a slope. So like if my derivative, and we'll just call it like f prime of x, is equal to 4x minus 1. If I want to find the slope of the tangent line at x equals 1, what you're doing is you're computing f prime of negative 1. So I'm just going to plug in a negative 1 into the equation that I got. And not only am I getting an approximate slope, but I'm getting the exact slope, so to speak. So on Delta Math today, what you're going to have are slope of tangent lines, and then writing the derivative as a limit in just sort of that limit form. I will show you what I mean by that. So the equation of the slope of tangent lines, that one, you're going to be doing the limit definition, and I'll just kind of show you the solution here. So what they did is they plugged in the x plus h, just like what we did, except they didn't do it on the side, like what we did. This is negative 8 times x plus h plus 8, and then the minus the negative 8x plus 8. And they were just left with a h term, and those h's were able to cancel out. And they were able to, and actually, I think one thing that is helpful says find a slope of the tangent line at x equals to 11. Well, actually, it just becomes negative 8. And this kind of makes sense because an Algebra 1 kid would say that the slope is negative 8. And then I'm going to give you writing a derivative of a limit with the h approaches 0 only. So this says you do not need to simplify your answer. So like on this one, I would have the square root of x plus h minus 3 minus the square root of x minus 3. Now, if you want this whole thing to go in a numerator, put a parenthesis on, just make sure that you are clicking on the outside here. So so that the parentheses can include the whole expression. And what this is just doing is it's just checking that you can set up a limit definition of a derivative. And same with like this one too. So this says, given the function f of x equals to, and I'll just kind of show you the solution here for this one. It's pretty much the same type of exercise, except you're going to be substituting in the -7 for x. So if we wanted to kind of like, do this one, it tells you to set it up, but don't simplify. So, what's really going on here is you'll have the 4 times x plus h to the 4th minus 2 times x plus h to the squared minus 4x to the 4th minus 2x squared over h. And you would put it in like limit notation. So like limit as h approaches 0. And then all what they're doing is they're putting in that -7 and be careful with the parentheses here, especially. Now, if I asked you to do this like algebraically and simplify, you'd be in for a lot of polynomial multiplication. But even just having this set up would show that you have a pretty good understanding of the limit definition of a derivative. So be prepared to be challenged on these exercises. And I'll try to go, pretty straightforward on the assessment. Maybe have you do like, a simple limit definition, and then kind of a setup like this as well. But I think it is really good for you guys to see the limit definition of derivative so that you can connect it with the limits that we were doing before.